Okay, I guess it's recording then. So we have a null hypothesis, H sub 0, and we have an alternative hypothesis. The alternative, okay? And the null hypothesis always has some kind of equal sign in it, and the alternative always has is identical to the null hypothesis, except the equal sign has been replaced with either a not equal sign, a greater than, or a less than sign. Okay. So when we do a t-test, okay, so today's t-test we are going to do a t-test for comparing independent samples. And the idea behind today's t-test is that we want to know if if my data consists of two independent samples, what kind of conclusion can I make about their respective populations? So the idea here being we have sample 1 and we have sample 2. Sample 1 has a mean of y bar 1. Sample 2 has a mean of y bar 2. Okay. These two sample means, y bar 1 and y bar 2, probably are not exactly equal. And we're assuming sample 1 comes from population 1, this large entity that we cannot observe directly. And sample 2 is coming out of population 2, some other large entity that we cannot observe directly. So the hypotheses that we propose here, our null hypothesis will be that mu1 is equal to mu2, meaning that the two populations have the same population mean. The two respective populations. Oops. Sorry. Have the same mean value. Okay. And then the alternative would then be that the two respective populations do not have the same mean value. Now, we can say use the not equal sign here, or depending on your situation or your research question or whatever you might have, you might choose to use a greater than or a less than sign. Okay? But this is the general idea that we have going into a t-test for comparing independent samples. Okay. Let me just save this. Okay, so I said once, so going back to all of hypothesis testing, we said that you have your two hypotheses, your null hypothesis and your alternative hypothesis, and we calculate something called a p-value. Okay, and the p-value is the probability of observing our data or something more extreme if we assume that the null hypothesis is true. Okay, so the p-value is a probability. And so for the t-test, okay, we said our null hypothesis is that mu1 is equal to mu2. Okay? Or another way I could write this, and these are equivalent ways of writing the same thing, is to say that mu1 minus mu2 is equal to 0. Okay? And if we were to put these into words, this one says that the two mean values are equal, and this one says that there is no difference between the two mean values, right? The difference between the mean values is 0. So to say that they're equal is to say the same thing as there's no difference. I guess I should just point out, we never write that H0 or the null hypothesis is equal to 0. We always write the null hypothesis colon is this statement that mu1 minus mu2 equals 0, or is that mu1 equals mu2, or something like that. So the null hypothesis itself is not a number. It is a statement about population parameters. Okay? And note that we're using mu in the hypotheses and not y bar or anything like that. Okay, so the hypotheses are always statements about the population. Okay, so use mu, never y bar. Okay. Also, our textbook chooses to use y bar as the sample statistics. If you take a future class, another textbook might choose to use x bar instead. It's no big deal, okay? Just different textbooks have different preferences for which letter to use. Okay, so for the t-test, this is our null hypothesis, and so if we assume that the null hypothesis is true, when we take two random samples, okay, we would expect that y bar 1 and y bar 2 to be close in value. Okay? So, for example, let's say we did a hypothesis test and we wanted to know is the average IQ of men in the United States and the average IQ of women in the United States, are they the same or are they different? Okay? Now, the null hypothesis in that situation would be that the average IQ of men in the US is equal to the average IQ of women in the US. So we would expect, so the populations have the same average IQ. Okay? So if I take a random sample of men and we measured their IQ scores, and we took a random sample of women and we measured their IQ scores, we would expect the sample, the average of the men's IQ in our sample to be very close to the average of the women's IQ. Okay? So maybe our sample of men produce an average IQ of 99 points. Okay? And maybe our sample of women produce an average of 101 points. Okay? We would expect that fits with our expectations. Okay? We wouldn't expect them to be exactly equal, but we expect them to be close. And I would say, 99 versus 101, probably not a big deal. Okay? However, if we took two samples and one sample ended up having an average of 90 and the other sample had an average of 115, that would be rather surprising to us. Okay? So anyway, going back to this, just for all t-tests, we would expect that y bar 1 and y bar 2 to be close in value. Okay? But only on very rare occasions would y bar 1 and y bar 2 actually be equal to one another. Okay? Be equal. So we have something called an observed difference between the sample means. Okay? So in all other cases, which is pretty much all the time, we would have what we call an observed difference between, I'm going to put sample in parentheses, sample means. Okay, so y bar 1 minus y bar 2, this is our observed difference. Okay. So just because of sampling, we're not going to have 0 here for this observed difference. And so the question is the observed difference that we're seeing, is this significantly different from 0? Or could it just be a result of random sampling? Okay. All right, and so this brings in the concept of statistical significance. And so we'll go through the test, but basically if y bar 1 minus y bar 2 is large, that would probably lead us to the conclusion that the difference is statistically significant. Okay. The idea being that y bar 1 minus y bar 2 is so large that it is highly unlikely that it resulted from the process of random selection alone. Okay. Okay. All right, and so to answer this question, we're going to employ the use of the t-distribution, which it all stems back to we had sampling distributions. Okay, so sampling distributions was the idea that you take a bunch of samples. We know that the distribution of sample means follows a normal distribution. Okay, and we skipped this section in the textbook, but if you have if you combine random variables that are normally distributed, the resulting combination is also normally distributed. So if if random variable A comes from a normal distribution and random variable B comes from a normal distribution, then the quantity A minus B, which is technically another random variable, that also comes from another normal distribution. Okay, so I know we kind of skipped that earlier on in the course. I think it's okay that we did, but we're going to use that result, and we can say that the quantity, so from our understanding of sampling distributions, okay, from our understanding of sampling distributions, if the null hypothesis that mu1 minus mu2 equals 0 is true, then we can say that the quantity y bar 1 minus y bar 2 also comes from a normal distribution. Or not also, will come from a normal distribution. And the properties will be that the mean is equal to 0, and the standard deviation is equal to the square root of sigma 1 squared over n1 plus sigma 2 squared over n2, all square rooted. Okay. But we run into the problem, again, of not knowing what sigma 1 and sigma 2 are. So we're going to use the standard deviations of the sample. Okay, and we're going to end up looking, it's going to look a lot like when we did confidence intervals. Okay, but again, we do not know sigma 1 or sigma 2, so we will use S1 and S2 as substitutes. And as a result, we have to compensate by not using the normal distribution, but using the t-distribution as well, okay? And we compensate for this substitution. Using the t-distribution. Okay. So now we say y bar 1 minus y bar 2 comes from t-distribution with mean equal to 0, standard deviation or standard error equal to the square root of s1 squared over n1 plus s2 squared over n2, and degrees of freedom, or I'll say approximate degrees of freedom, equal to n1 plus n2 minus 2. And again, this is an approximation for the true degrees of freedom, which is a complicated formula that we don't need to get into. Okay, so this is what we have. Are we doing okay? All right, we'll take that as a yes. Okay. All right, so let's try out an example. Okay, so example 1. Okay, we will take the 2 random samples. Okay, sample 1. We will take men. Sample 2, some women, okay, and we will have, let's say we have a sample of 15 men, a sample, so I'm going to say N1 is 15, N2, 18 women. We will measure their height, okay, so y bar 1, the average height of these 15 men, let's say, is 69.7 inches tall. Y bar 2, let's say for these 18 women, is 64.5 inches tall. The standard deviation for the men's height, we will say is 2.9, and the standard deviation for the women's height, we'll say is 3.0. Okay. And we want to know, do our samples provide evidence that the average height of all men is higher than the average height of all women. Okay. Oh, I guess I should say both of these samples, oh, I did say that, random samples. Okay, so these are randomly selected men, 15 randomly selected men, 18 randomly selected women, and we want to know, do our samples provide evidence that the average height of all men is higher than the average height of all women? Okay, so our null hypothesis will be that mu1 is equal to mu2. The null hypothesis always has an equal sign. So even though the question is saying, does this provide evidence that it's higher, you're not going to put a greater than sign in the null hypothesis. Null hypothesis, you always got to put an equal sign in there. So the alternative, I'm going to do mu1 is greater than mu2, because that's what this question is asking. Is the average height of all men higher than the average height of all women? Okay, and it might feel weird having an equal sign matched up with a greater than sign. You might feel like, well, if I have greater than over here, maybe I should have less than or equal over here, or something like that. Okay, that's just not how it works. You just you always put an equal sign for the null hypothesis, and then you can have a greater than, less than, or not equal sign. And so, you know, what do we do if we end up getting, or not, we end up getting the, you know, what happens to the other side? Well, in this case, we just ignore any results that might point in the opposite direction, okay? And so, whenever you have, and this will be come into play later, but I'm going to just point this out now, okay? So, if you have a greater than or a less than sign in the alternative hypothesis, this is known as a directional test. It is a directional, or also known as a one-sided test. And we'll do an example with a non-directional or two-sided test, and that's when you have the not equal sign. But if you have greater than or less than in the alternative, you have something called a one-sided test. Okay? And so whenever you have a one-sided test, you have to do kind of a common sense check, and it's called check for directionality. Okay? But it's kind of, I like to call it just a common sense check for directionality. And so anytime you see something that says common sense, it's kind of a warning that it's easy to forget about, right? You just say, oh, or I don't know, they say if common sense is so common, well, you know, why doesn't anybody have it? But so what if the question instead said, do our samples provide evidence that the average height of all men is lower than the average height of all women? In that case, my null hypothesis would still be the same, but my alternative would have mu1 less than mu2, right? Okay, so if our question said, do our samples provide evidence that the average height of all men is lower than the average height of all women? So actually, I guess I'll write this off on the side here. Okay, so just alternative scenario. Okay, so let's say question said evidence that average height of men is lower than average height of women, ... Okay? And in that case, everything would be the same. Null hypothesis is still mu1 equal to mu2, but the alternative, so let me just rewrite this, would be that mu1 is less than mu2, okay? But when we look at our data, the data show what? Y bar 1 is equal to 69.7, and that is greater than Y bar 2, which is equal to 64.5. Okay, so when we look at our data, mu1 is not less than mu2. Y bar 1 is not less than Y bar 2. Y bar 1 is greater than Y bar 2. So in this question, do our samples provide any evidence that the average height of men is lower than the average height of women? The answer there is no. Our samples do not provide this evidence, okay? Okay, and then in that case, there's no real sense in continuing on with the statistical test. Okay, because the answer is no. You're not going to have evidence to support this conclusion. And so that's what I call the common sense check for directionality. I think it makes sense to do that, but, or actually not make sense to do that. It is important that you do that, and the resulting conclusion should make sense in that regard, but it's oftentimes easy to forget about. Just if you have a directional alternative, you should check to see if it even makes sense to even ask that question. Okay, so anyway, this is what we have. Let's continue on with it here, and so actually let me just copy this stuff. Okay, so to answer a question, our null hypothesis, mu1 is equal to mu2. Our alternative is that mu1 is greater than mu2. So we did our check for directionality. And when we check for directionality, the answer is, does our data match the directionality of our alternative hypothesis? Yes, our data matches the directionality of the alternative hypothesis. So the answer here so far is maybe, okay? Okay, so our data matches the directionality of the alternative. Okay, so now we can continue on. So we take our observed difference. What is our observed difference in sample means or between sample means? So our observed difference would be y bar 1 minus y bar 2, which would be equal to 69.7 minus 64.5, and I get an observed difference of 5.2 inches. Okay? So actually, we'll just say 5.2. Is 5.2 significantly different from 0? Or is it possible for the null hypothesis to be true, and by random chance, I happen to get a sample of 15 men, or 15 people where the average was up here, and a sample of 18 people where the average was down here? Could that happen by random chance? I mean, technically it could, but how likely is it? Okay. So we said this quantity comes from the t-distribution with a mean of 0 and we have the standard error, okay? And we want to know, well, what's the probability of ending out at 5.2 or something more extreme? And in our case, more extreme means a difference where mu1 is even more greater than mu2, so I'm going to have 5.2 or something larger than that. So our standard error, so essentially I'm going to be calculating like a z-score, but it's a t-distribution, so my test statistic t is going to be 5.2 minus the mean of 0, okay, which I guess isn't necessary, divided by the standard error. Okay, my standard error is given by this equation, s1 squared over n1 plus s2 squared over n2. So I get, gotta punch this into the calculator. Alright, so let's try this out. 2.9 squared divided by 15 plus 3.0 squared divided by 18, and I take the square root of that. Okay, so I get a standard error of 1.0299, or 1.03. pretty much. So my t is going to be 5.2 over 1.03. Okay, I get a t score of 5.05. So I'm not standard deviations, but standard errors away from 0. Okay, so that feels pretty significant. Okay, and we can look this up in the t-table. Okay, so the t-table works different from the normal distribution. Okay, but anyway, I get a t-score of 5.05, meaning I'm 5.05 standard errors away from 0. So already we get the sense that this is a large difference. Okay, so it seems like it would be pretty statistically significant. Okay, so let's just let me just show us how we would use the t-table. So how many degrees of freedom do I have? I have 31 degrees of freedom, right? N1 plus N2 minus 2. So approximately, I have 31 degrees of freedom. So we would go to our t-table. Working here. And let's zoom in. Okay, so we're going to just use 30 degrees of freedom. That's good enough. Okay. And here, actually, I think it's worth just taking a pause and noting how the t-table works. Okay, so just, I don't know, put a little break in your notes here. So let's using the t-table, we'll do that right here. Just because it's a little different from using the normal table. So let's do, I'm going to draw a big curve here. And so the t-table, t-distribution, the table that you have, starts off with 0, and with the normal table, you looked at the z-score and it gave you the area to the left. Okay. With the t-table, it gives you the area to the right, or the upper tail probability. And let's just take a look at this row with 30 degrees of freedom, okay? Our very first number, let me see if I can copy this. Where's the snipping tool? Okay. So I'm going to copy this column headings. Put this down here. Let's increase that a little bit. Can you guys see that? I hope. And then let's zoom in and also snip this. Okay, so I'm just copying this row here, and I hope, shoot, I hope I can get this to line up. Okay, well, that's good enough. Okay. So what we see with 30 degrees of freedom, the very first number that shows up is 0.854. So what this means is that if I draw a line at 0.854 right there, and I shade everything to the right, where's my paint bucket tool? So if I shade everything to the right of 0.854, the amount that I have shaded, this shaded area is 20%, okay? So 0.20. This is how much I have shaded. Now, if I go further away from 0, and I go to 1.310, out to here, so further away from 0, 1.310, and I shade everything to the right there, then the amount that I've shaded now is 10%. Okay? So this 20% also includes, so this is everything to the right, everything to the right of 0.854. 10% is everything right of 1.310. Okay? So we can see that as we get further and further away from 0, so if I go all the way out to 2.457, so if I go all the way out here to 2.457, then the amount I have shaded to the right there is only 0.01. So a common question is, why do the numbers get smaller as our critical values, these are known as critical values, as the critical values get larger, why do our tail probabilities get smaller? And the answer is you're getting farther away from 0, so the amount that's available to shade into the right becomes smaller and smaller. Okay? So critical values get larger, but tail probabilities as we go this way get smaller. Does that make sense? So what if I drew a line not at 0.854 or 1.310, but what if I drew a line at 1.0? And I said I'm going to shade everything to the right of 1.0. How much is to the right of t equal to 1.0? Okay. Again, degrees of freedom equal to 30. What would you say? Well, you can try to interpolate, but you don't have to. We're just going to say we don't know the exact answer, but we do know it's more than 10% and less than 20%. Okay, so exact answer unknown. But that's okay. We just say I'm sorry, not T. Tail area is greater than 10%, less than 20%. And that's totally fine. When you use the tables in the back of the book, that's probably the best. That's the best you can do. Okay. If you want an exact answer, you can go to a computer, type it into the computer, and the computer can give you an exact answer. But a lot of times, just an approximate answer, kind of giving you something like this is good enough to answer your question. Okay, so that's how we use the t-table. So if we go back a page, where is it? Okay, so if we say our t-distribution, or going back to the problem that we were working on, if our resulting statistic 5.2 has a t-score of 5.05, what is the resulting tail area? 30 degrees of freedom. Okay, so 30 degrees of freedom. I'm now looking for the value 5.05, and we see that what? 5.05 is beyond what the table provides, right? The table says if you go all the way out to 3.646, then you have then you have 0.0005 in your tail. If we go even further away, what can we say about the area in our tail? It's less than this. We don't know exactly how much, but we do know it's going to be less than 0.0005. Is that okay with everyone? Okay. So, so we go over here. So when we look this up in the table, look up in t-table, we get that our tail area, we don't know exactly how much it is, but we do know that it's going to be less than 0.0005. So this is known as our p-value. Our p-value is going to be less than 0.0005. What does it mean that our p-value is less than 0.0005? So what is a p-value again? It's the probability of observing our data or something more extreme if the null hypothesis is true. That's kind of the definition that I wrote. What is it? What is the p-value in the context of this problem? I'm sorry?
So it means it's very unlikely.
Yeah, it means if we were going to assume that in our world men and women have the same average height, is it possible for a random sample of 15 men to have an average and a random sample of 18 women to have a difference in the sample heights to be 5.2 inches? Is that possible? The answer is yes. Technically it's possible, because with random sampling almost anything is technically possible. But is it likely? No, it's incredibly unlikely. The p-value being less than 0.0005 says that's how unlikely it is. It's the probability that random samples are going to produce this kind of difference is less than, what is this, 5 in 10,000? Okay, so less than 1 in 2,000 chance of this happening just from random sampling alone. So at this point we can choose to believe either we just happen to have this really strange freak samples, or our initial assumption that men and women are the same height is wrong.
So what is the p-value in this case?
So the p-value is less than 0.0005. And so that it would be that is the probability that two random samples produce a difference of 5.2 inches if the respective populations have the same mean. Okay? So if men and women truly had the same average height, or if you just had two groups that have the same average height, what's the probability that two random samples would be so different as to produce a difference of 5.2 inches? The probability of that happening from random sampling alone is less than 1 in 2,000, is what this is saying. Okay, so our conclusion then would be, so our p-value, again, was less than 0.0005. So I guess I'll write that. Okay, so our p-value states that, or this, okay, so the probability that two random samples would produce a difference of 5.2 or more between sample means by random chance alone is less than 0.0005. Okay. Is that legible? And random chance alone means that mu1 and mu2 are equal. Okay? So because this is so unlikely, and yet we have data that, and yet we observed this data, this gives us reason to believe that our initial assumption that our null hypothesis mu1 is equal to mu2 gives us reason to believe that our initial assumption that this and this are equal to each other is wrong. Okay, so we conclude that our data provides evidence that the average height of men is higher than the average height of women. Okay. It feels like a lot of work for something we already knew, but this demonstrates the process, okay? And it could be used for any time you're trying to compare the means of two populations where the means of those populations are unknown. So if you don't know, is the average orange bigger than the average apple? Maybe, maybe not, okay? Well, that's actually a very difficult question to answer because it's difficult to get a true random sample of oranges and a true random sample of apples. But if we were able to obtain truly random samples of apples and truly random samples of oranges, then we can answer that question. So maybe you could say, maybe at this particular grocery store is the average apple larger than the average orange, okay? And you have to decide how to define larger. Is it by weight or by volume or whatever? But you can then, by taking a random sample of even, 15 apples and 15 oranges, you might be able to answer it, okay? It could also turn out to be that it's inconclusive. And then if it's inconclusive, then you either have to gather more data or just be satisfied with an inconclusive answer. Okay, so maybe I will give you guys an exercise here for you to try out on your own. All right, so let's say, is the average, what's the average size of an apple? How big is your average apple? Weight of an average apple? Does anyone know? Apple. Average size. I'm getting results on Apple products. Okay. All right, we'll ask a different question. Okay. We'll say, is the all right, I'll just make up two things. Average XYZ larger than the average JKL. All right. So somehow you manage to obtain random samples. Okay. And this is really the hardest part in all of this, on a practical setting. Okay. Oh, that's loud. So in a practical setting, obtaining the random samples is actually difficult. For writing test problems and textbook problems, it's easy. You just say you got a random sample. But practically, this is hard. And if you can't get a random sample, you always have to keep in mind that the results of your study may be invalid if it turns out that your samples are not representative of the population. Okay, but anyway, random samples. So we get we have n equal to 12 XYZ, and the y bar of these things is 142 with a standard deviation of 25. So I'll put ones on these, and then for JKL, the sample size will be 10. We get 10 random ones of these. Y bar 2. The average is 150, and the standard deviation will be 18. Okay, go ahead and try this out, and we'll go over our answer. Yes. Okay, is the average XYZ larger than the average JKL? Okay, so correctly, as you guys noted, here the larger, so when we set up our hypotheses, you'd have mu1 equal to mu2 and mu1 greater than mu2. But when you look at your data, as you do a directionality check, this fails the directionality check. Directionality check. Okay, this fails in that, if anything, our random samples seem to indicate that XYZs are smaller than JKLs. Okay? So let's change this question into, is the average XYZ smaller than the average JKL? Okay, can we make this conclusion based on our random samples? Okay, so I'm going to pause our video again, and so now our alternative hypothesis, we'll say mu1 is less than mu2, and then so carry it out, because this time the directionality check will match our data. Over our answer then. Okay, so we have written our null and our alternative hypotheses as so. We take a look, we find our observed difference, which will be 142 minus 150. I get an observed difference of -8. So whatever units we were using for measuring size, grams or kilos or yards, whatever. It's the average XYZ. So right now, our sample of 12 random XYZs has a sample average 8 smaller than the sample over there. Okay. Our standard error would be the square root of 25 squared over 12 plus 18 squared over 10. I'm getting 9.19. Is that what we got? So far, so good. Okay, so our test statistic T would be -8. So under the null hypothesis, we would expect a difference of 0. So I guess you could leave off this -0 if you wanted, because doing a plus or minus 0 doesn't do anything to your number. And then you divide that by 9.19. So I get 8 divided by this, -8, I get -0.87. -0.8704. If I preserve the decimals in the other part. Okay, how many degrees of freedom do I have?
20.
I'm getting 20 degrees of freedom, approximately 20 degrees of freedom. 12 plus 10 minus 2, I have about 20 degrees of freedom. So we're going to look up 20 degrees of freedom, and we're going to look up -0.8704. Okay, so when we go to 20 degrees of freedom, we only have positive numbers in the table, okay? But the t-distribution is symmetric, okay? So I can just ignore this negative and pretend like I'm looking up positive 0.87. Okay, and so what do we see? The first number we have is 0.86. So we know that 0.87 is further away from 0 than 0.86. Not by much, but it is further away. But it's less than 1.325, okay? So our tail area will be less than 0.20, but greater than 0.10, or if you wrote it the other way around, that's fine, okay? And our tail area is probably much closer to 20% than it is to 10%. If I had to guess, I would say 19%. But again, we don't need to try to get precise. All we have to say is that our tail area is between 10 and 20%. If your test statistic ended up one of the numbers, the critical values, like if we got 0.860, then you know your tail area is exactly 20%. Okay, but that doesn't happen very often. Okay, it doesn't happen very often, so when it does, it's rather exciting for me. But And it's okay, you know, that even though we're getting 0.87, which is only just ever so slightly bigger than 0.86, we can just say it's less than 20%, more than 10%, okay? Probably very close to 20%, but it's okay. We don't have to worry about that. Okay, and so we want to, so in our little picture, I would be centered at 0, and I'm going down to, I'm observing a difference of -8. And we say, how much is in this tail? Over here, the area in our tail is between 10 and 20%, and that will be our p-value. So our p-value is also less than 20%, greater than 10%. Okay, and so this question is, well, could the result of getting 142 over here and 150 over here have happened by random chance? And the answer is yes. And the probability that it happened by random chance alone is something between 10 and 20%. So that's a non-negligible probability, okay? It's about, you know, rolling a die happens 1 in every 6, so that's about 16 or 17%. So this happens almost as often as that, or more often, maybe a little less often, but probably more often than that. So it would be unwise to say this provides conclusive evidence that XYZs are smaller than JKLs. So we're going to just say our p-value is not small. So we will not say that we have evidence that XYZs are smaller than JKLs, okay? So I guess in just generic forms we would say we do not reject the null hypothesis, and we can also say we do not have evidence to support the alternative, HA. Okay, let's take a break here, and then